Thank you very much. I'd like to definitely thank Tara and Clean Air Task Force for sponsoring the work and inviting me here, and also Quays Energy, my current company. Tara caught me at a transition as well. Like Tony, I was leaving conventional geothermal company Circ Energy and returning to Superhot rock EGS, which is something I'd first proposed at Newberry back in 2018. So this really allowed me to get back into Superhot rock and EGS, going through the exercise of looking at heat extraction again. And I think the exciting part is it's the progress in that time period from 2018 to 2024 has been huge. And we went first. Owen and I wrote this proposal, or this report first. Tony and Suri's reports was later. And just the progress there has been really incredible as well. I think that, and so you'll see in my talk that I'm going to be referencing some of the drilling and casing problems. We've just seen a great update from these other guys. Okay, so and also I'm going to be a little more generic in my talk because it was an earlier talk, and we actually haven't exactly made some definitions here. So what is Superhot rock? I think that we have actually two competing definitions at the moment. We have the global definition, which or my definition, what you call it, which is rock formation at a temperature higher than 375. That results in an enthalpy of over 2,100 kilojoules per kilogram. Here in Iceland, and that's basically this regime here. So, and this is pressure independent. So we're not talking about supercritical necessarily, because there's a pressure definition there as well. That is more enthalpy than, like, 3 times as much enthalpy as binary plants, which is really a lot of our competition in the U.S. at least. The Fervo kind of solution for EGS right now. And higher enthalpies in a lot of conventional geothermal fields. In Iceland, they're blessed here, of course, with very high enthalpies, and they prefer a definition of an enthalpy greater than 2,800 kilojoules per kilogram, and that actually allows as the resource flows up the well to stay completely in the outside of the liquid and vapor phase. So that prevents this vaporization, condensation of which will cause corrosion problems. So I think it would be great if we could all have this higher enthalpy definition, but I think for now I'm just going to stick with the 375 number. Just if we look at EGS or geothermal projects worldwide over the years, there actually have been quite a few wells, over 20, drilled to this temperature barrier of 375, all the pink dots here. IDP2 is I think that dot. Very few of these were drilled into supercritical conditions, though, because of the pressure. So a lot of these wells are quite shallow, shallower than 3 kilometers. And you basically need 3 kilometers of pure water to create supercritical conditions. So also some of the salt and sea wells have been drilled, but they're very high in salinity. They've been drilled to these temperatures, but the critical point of water also depends upon the salinity. So that critical point is way down here at say, deeper than 5 kilometers if we've got 10% salt. So once we get deeper, native supercritical fluids may be rare, but once we go deeper and deeper, there will be supercritical fluids in the reservoir, although maybe not flowing to the surface. So just kind of what are our goals if we're going to actually build a Superhot rock system? What are the goals of our first of a kind and nth of a kind? So what we're really aiming at is 20 megawatts per production well or greater. This enthalpy greater than 2,100 kilojoules per kilogram. Sustainable field operations of 20 years or more. So Suri talked about how do we build a well that'll last that long, and that's going to be very important. And levelized cost of electricity of less than 50 megawatts, $50 a megawatt hour, and that's what's going to allow us to scale globally. We also need low risk from induced seismicity. So that we all kind of know some of the stories of projects that were killed by induced seismicity. Those first 4 goals are going to be required for our nth of a kind. Our first of a kind project is probably going to achieve maybe none of those, but we do need to, just a reminder, we always do need to be having low induced seismicity risk, because otherwise we'll lose our social license to operate and continue working. This is kind of a typical, I think we've all drawn these diagrams of, injection well, something, and then production well. So this is really my job, is to understand what are we going to do there. So this is the part where the first two talks talk about how do we do this, how do we get to here, but now the question is what do we do here? And of course, we've all created these diagrams without any specification of what's going on there. So that's what I'm going to try to do, although I think I have probably more questions than answers. In my paper, and this was a GRC paper, we published, my co-author and I, Owen Callahan, published back in October, I guess. We actually go through in a lot of detail on 14 different categories of the gaps. And some of these gaps are overlapping with the previous two talks we've had here today. I'm not going to cover all those, but I will just kind of hit some of the highlights of some of the what we identified as the status and gaps. But first, let's just kind of, I think in Iceland, this is important to say, why do we need EGS? Because here in Iceland, it's not clear that we do need EGS. It's really all about what in situ permeability are as a function of depth. And so you really need, say, greater than 100 millidarcy for an economic geothermal wells. These are permeabilities from both wells, so well tests, and permeabilities from geothermal fields, and basically these are from numerical reservoir models, the values that they've used to history match production in numerical reservoir models. So Krafla, I think, is probably this dot here up at above 10 to the negative 12th meters squared permeability. But in general, as we go deeper and deeper, this curve here shows work from Skybeck or Manga et al. In 2012, what the typical permeability is with depth. And as we get down to, say, 3,000 meters, we're in this range, if the crust is undisturbed, of less than a millidarcy, and it's definitely not economic well flows. So we've got to have a way to get out to what Manga characterized as disturbed crust. So basically, we know in places where there's seismic activity, high strain rates that were at a curve like this, if we can get from the undisturbed permeability curve to the disturbed permeability curve, then we can create an EGS system. And so basically, you've got to go 3 orders of magnitude improvement in permeability. And we've done that just as a geothermal community. Salts, GPK 2 and 3, basically improve from sub-economic to economic. There's Hijiori is another example. All these pink arrows show EGS projects where we moved the permeability. The Newberry EGS project that I was involved with back in 2010 to 15, we did actually increase the permeability by about 3 orders of magnitude. Problem is we started so low, we weren't really able to get all the way to an economic flow rate. So we have to find better ways to stimulate wells than we tried in the past. And especially once if we really want to do geothermal everywhere, we're going to have these non-conventional approaches. So here's just cartoon, really, of some different models that have been proposed and executed. So far left over there is the closed loop solution that Ever is really a champion of. They're doing this in Geretsried, Germany. I think, so one thing I'm just listing here is surface area, so just kind of track that. The biggest problem that I see is that you just basically don't have much surface area for conductive heat mining. So it's something like 10,000 square meters of surface area, even if you drill 72 kilometers in creating this loop. So what that surface area means is that you're going to cool off very fast, and you're just not going to be able to be very effective heat extraction. Another method that's been tried many times is what we call hydroshearing or shear stimulation of existing fractures. This is what we did at Newberry in 2014. It's what was done at Salts. This has been done at temperatures from 150 up to 300 degrees C. It's really hard to control or quantify the total surface area created in this sort of system, and I think that's probably its biggest weakness. You're very dependent upon the geology. You can do things like you can try to do multi-zonal isolation of natural fractures, but you're still dependent upon the geology. Planar hydraulic fractures. Now, this is something that's been proven very well, I think, at Project Red by Fervo. up to a temperature of 200 degrees C. They're pretty limited at that temperature, though, right now because they're using off-the-shelf equipment. But now this is getting up to 1 to 10 million meters squared of surface area, especially if you have 100 to 200 of these planar fractures connecting the two wells. And that's what's going to allow this system to be a little more sustainable at higher temperatures. Now, they still haven't proven the long-term stability or sustainability at Project Red. It's only been operating about 6 months. And the other problem they may have is their wells are pretty close together, only about 100 meters apart. So there's a limit of the area. Another option that's been proposed is hybrid fracture network. So basically creating these planar fractures, but relying more on the natural fractures to connect your two wells. This is part of the plan that Mazama will be performing at Newberry this year and next at a temperature up to 310 degrees C. And so this is the difference between these two is partly operational, but it's partly philosophical. You know, what is the importance of those secondary fractures in making connections? Fervo's just made this kind of statement that the planar fractures are all that really matters. But that debate is still occurring in the oil and gas industry as well. It's the importance of secondary or off-axis fractures. I'm going to be talking a little more detail about kind of a fourth or fifth method of extracting heat. And that's, you know, what about the special properties of ductile rocks or nominally ductile rocks? And this is work that Sam Scott, who's here in the audience, has done more recently. Can we get just a large volume of rock to fail along a more diffuse network and taking advantage of the rock properties? You know, just where are we kind of backing up a little bit? Where are we as far as heat extraction with superhot rock? You know, and so what are the different categories? So I'm going to talk a little bit about the fracture propagation and reservoir modeling, lab testing at reservoir conditions, site selection, and well completions and directional drilling. I'll try to fly just right over there because we've had two excellent talks by real experts at that. Well logging's an important, basically characterizing the well, the actual stimulation itself, induced seismicity, as I said, is very important, and diagnostics and characterization. So as we've already learned, we've reached superhot rock with conventional drilling many times, 20 different wells. Those well completions are challenging. The wells have not lasted. And really, EGS and low permeability superhot rock has not yet been attempted. There's one exception to that is really a geysers project, which I'll talk about, I think, just briefly. So there is, I think, unlike the previous two talks where it's just engineering, I think there is some basic science we still need to do. And one area that we identified is, you know, there is a good analog for superhot rock, fluid flow, and fluid dynamics, and rock fluid interactions. And that's, you know, that's geology that's exposed in ore deposits and tectonic zones. And I think we can learn a lot more from looking at reservoir analogs and interacting with economic geologists, metamorphic and igneous petrologists, and people in the geothermal industry. So there's, you know, we see a lot of evidence for cycles of brittle ductile deformation in just geology. And there's an example here from the Alpine Fault in New Zealand. So let's just talk about what's been done in the brittle to ductile transition. So at these temperatures above 400 degrees C. So first question is, where is the brittle ductile transition? What temperatures? And there has been tests at EPFL in Switzerland by Maria Violet's lab, basically looking at the onset of ductile deformation. And at laboratory strain rates, that's occurring at 800 to 850 degrees C, depending on whether it's mafic rock or a more silicic rock like a granite. That translates to a tectonic strain rates of 10 to the negative 14 seconds of, say, 300 up to 650 degrees C, depending on silica content. So we know where that occurs, but, you know, when we're doing EGS, we're probably at strain rate somewhere between. So the actual brittle ductile transition is strain rate dependent. So we're somewhere between those temperatures. So there's that work has been done. Some work in Japan by Watanabe's lab they've seen that at these temperatures, if we are at 200 degrees C, and simulate a well and stimulation in a well, fractures are, as we expect, planar. They're requiring very high pressures, so twice the breakdown pressure is twice the confining pressure. Once we get up, once they did tests up to 450 degrees C, up into the supercritical nominally ductile range, the rock failed in a more diffuse way. Pore fluids went out into the rock sample and caused this diffuse cloud network or cloud fractures. And also the rock was far weaker, failing just a little bit above the breakdown pressure. So the question that Quaise Energy, my current company, and Sam Scott have asked is, how can what if we leverage this laboratory result at a larger scale? Can we better understand or better create a model for heat extraction? So I'll talk about that shortly, but first let's just talk about the gaps in rock fracture mechanics in this brittle ductile transition. And I should also add fluid. I think implicitly here is fluid rock interactions as well. So, what are the impacts? If we're injecting cold water, it's going to heat up. It's going to be cold to start. It's going to become supercritical as it goes out into the formation. What are the impacts of that fluid on the rock itself, the fluid dynamics? Things. Surrey just kind of pointed out that the longevity of well materials and engineered permeability is a gap that we need to study, and then fracture mechanics and diverse lithology. So I think there's this assumption that everywhere you go deep enough you hit granite. It's not true here. It's not true everywhere. It could be basalts. It could be metamorphic rocks. So we need more diverse lithologies tested. So we need to involve facilities beyond the oil and gas and geothermal industries. Mining companies have done some of this work. So they're very interested in that as well. And looking around globally to see what are the facilities that may be valuable for doing these sorts of tests. And geologic analogs for reservoirs and fracturing, I think, are another good way to get into the rock and fracture fluid dynamics in the brittle ductile transition. And that data is important for, that field data is really important for our modeled validations. We're working with a flow reactor at Oregon State University, installing one to be able to start doing some of this tests. And there's other groups as well beginning to work on these problems. So modeling, there's kind of two types of models that I think are important for EGS. There's the fracture propagation models. Most of the software for fracture propagation was designed and validated for oil and gas fracturing. So, for shales, basically at lower temperatures. So we need models that allow us to do fracture propagation. We also need updated models for reservoir models. So there are codes for research codes like TUF that work at these temperatures, but those are basically research codes still run by laboratories, national labs. There's not really commercial codes available. This is just an example of a fracture propagation here on the right model by Mark McClure on the forge fracture. When he first did his model, and this is kind of just showing the status as far as predictability in a new regime. So when he ran his fracture propagation models with his default parameters, his prediction was these chimney-shaped fractures going up 1,000 meters. He was able to history match by changing fracture toughness and several other parameters to get something that looked like the actual fractures. But there's a pretty big difference between his a priori prediction and his history match. And so just and we don't have anything to history match yet in Superhot rock EGS. So we don't this is the kind of problem we might have is a model prediction looking something like that, but this is actually what we're going to get. So we really need to do to go to the field and start doing it to be able to understand how our models are working. So I just promised earlier I'd talk a little bit about if we had cloud fractures occurring in an EGS system, what sort of EGS performance and system would we get? And this is modeling sponsored by Quaise Energy here at the University of Iceland by Sam Scott. So thanks to Sam for sharing these slides with me. So basically, he modeled a reservoir depth of 15 to 17 kilometers, formation temperature 400 to 500 degrees C, flow rate of 80 kilograms per second, kind of this typical number we use, one injector and two producers. So here's kind of the geometry, that central vertical injector and producers. And he found that if we have high fluid pressures and cold water, we can create and maintain a distributed permeability between the wells. And basically here we're seeing at different permeabilities, that permeability gets created. If you just pressure up the well, that we start to create permeability over kind of the month time frame, and then we can maintain that permeability and thermal output for up to 20 years. So, and the thermal output depends upon the permeability created. So the higher the permeability, the faster we're going to be able to mine that heat, or faster we'll see a thermal breakthrough. So at 100 megawatts thermal for 20 years, that represents about that 25 to 30 megawatts electricity if we assume 20% conversion efficiency. So that is a potential. This thought experiment, or this numerical reservoir model kind of says that there are ways to use a more EGS mining model that takes advantage of cloud fractures, which we've seen in the lab. Okay, site selection characterization. I think this is going to be something that the last talk's going to talk quite a bit. The only thing I wanted to kind of point out here, and Clean Air Task Force has done a great job with mapping depth to 450 degrees C globally. There's really one of the best maps out there right now. When we're starting our first of a kinds, and maybe our first 10 nth of a kind, we're going to be most likely in developed fields with wells of opportunities and depths to superhot rock of less than 6 kilometers. So Iceland, Newberry, magmatic areas most likely. The real prize, though, is to expand to energy brownfields like coal plants and replace the fossil fuels with superhot rock fluids, or superhot, to be able to replace their electricity generation with green generation. Once we start to go out to those places, we'll be using play fairway analysis, classical geothermal exploration techniques. So just some of the tools, and again, I'm not going to spend much time here because we've had talks which are far more specific and better than anything I've done here. But just the one thing I want to point out on why directional drilling. That's basically to be able to intersect the maximum number of vertical fractures. So that's kind of, I think, the default way of doing an EGS, the planar fracture model, but maybe not necessary, and we don't quite know for sure. But one good thing about this is, like Tony said, we can do a lot of cooling with insulated drill pipe, coated drill pipe, and we can. And that has been shown in places like Ever's been a real proponent of insulated drill pipe. Well characterization, so logging. The most important logs that we need, I think, for any sort of EGS are information on fractures, natural fracture systems, and stress orientations. This is a borehole image log from Newberry. This log actually could go all the way up to 280 degrees C. But if we want to get to 400 degrees C, we're going to have better tools with better heat shielding, or we can do a lot with cooling. Cool the well, maybe do logging while drilling on drill pipe. A big one is stimulation reservoir technology. How do we isolate zones in order to create the most fracturing along a wellbore? So what we've proven is open hole hydroshearing with diverter, or thermally degradable zonal isolation materials that Alterock has developed at 320 C. Cementing plug and perf has been done at, say, 200 degrees C. But there is a gap. Can we successfully place cement at above 350 C and do zonal isolation in superhot rock? And there's really no reliable high temperature perforation tool out there right now. So conventional, this style of fracturing is not going to be possible currently. But there are some solutions. We can do further material testing and development in labs, superhot rock durable cements, external casing packers developed by Welltech, basically to use all metal isolation, but to create different zones. And what we really need to do once we start have some of these solutions is go to the field for testing. going to go past that because Surrey did a great job there, and I can't add anything. Permeability creation. How do we? So the steps to that will be, initiating a fracture, growing a fracture. If it's a tensile frac, we're going to have to put proppant in it. So we need to find proppants that'll last, that will be stable at these temperatures. Quartz sand, typical proppant will certainly alter. So we're going to need to find other proppants, and we can test those in things like the flow reactor that we're going to be starting up soon. There's other solutions, which is, maybe we don't use proppant at all. Maybe we just hydroprop. Basically, have to operate at pressures that are high enough to keep the fractures open without it. And the other part of that is, as those fluids flow along fractures at these high temperatures, we may be dissolving rock. So create a silica problem for ourselves, but we may be enhancing the permeability and not requiring proppants. Demonstration projects, I think, are going to be critical for this because it's, we're going to be at a scale where it's really, you cannot prove anything in the lab. So demonstration projects, there's going to be one starting at Newberry shortly. Of course, IDP 1 and 2 and now 3 in the future are going to be important as well. These are examples, experiments, and they provide, I think, and one reason I think it's great to be here in Iceland, the opportunities for collaboration. So international collaboration. People have been working on this in Japan, Italy, everywhere. How can we work together? So some of the demonstration projects of the past and future, New Zealand, in Japan, Beyond Brittle, of course, all the projects here in Iceland, Descramble in Italy, and then Newberry is starting up. Well, it was a project 2010 to 2015, and then starting up here shortly. How much time do I have? 2 minutes. Okay, so just I think just quickly I wanted to cover, well, actually let me skip past this. I think probably a lot of people in this room are actually successful or familiar with some of the drilling that's been done so far. And it's, these are these wells that have purposely or by accident hit super hot temperatures. And there's really quite a few. So we really do know we can drill at these temperatures. And some of those places like Kakonda back in the 90s, the geysers demo in 2010, they actually drilled to 400 degrees C. Of course, the 2 IDP wells, well over 400 degrees C. And then a project that hasn't really come up much is this Descramble well in Italy, where they reached 520 degrees C. As far as the EGS side of any of these projects, at the Northwest Geysers, they actually did stimulate a well. Stimulating in the geysers is just about as easy as stimulating in Iceland. Just start adding cold water to it, and they were able to connect 2 wells at 400 degrees C. So that's kind of I would say that's the only time that EGS has been tried at super hot rock temperatures. At the Descramble well, they were able to drill the well, but they had problems with stuck pipe and bad cement, and there really never was a plan to stimulate that well. And then just I want to conclude, because as I pointed out earlier, induced seismicity is a key thing that we have to pay attention to in order to keep our social license for operations. And I think this is an area with enormous progress. I entered the geothermal business in 2008, just after the Basel fiasco, where induced seismicity became a huge deal for everyone in geothermal. And we built an induced seismicity mitigation plan for Newberry. And basically, this was the BLM protocol here, where you basically look to make sure you're at a site. Make sure you're not at a site where you've drilled into a normal fault that caused an earthquake in 1370 and destroyed the city. That's kind of the preliminary evaluation. And so let's not do that again, except, then they went and did it again in Pohang, Korea. But, communicate with your locals, have a traffic light system. And these things have all been really a huge amount of progress in the last 15 years, based on both oil and gas industry problems, but also geothermal projects in Europe mostly, but also in the U.S. So that's all I've got. Thank you.
While I give you guys a minute to formulate your questions, there was a footnote in there that I want to elevate here. Within Clean Air Task Force, we basically have two tools, policy and industrial acupuncture. And I'm going to set the policy part aside and point out that we're observing how we can help. This series of reports is intended to aggregate this information all in one place. But another area that we have identified is, of course, trying to understand where are these international laboratory spaces in which we can enhance with either further investment or just elevating what they can do. So my ask of this crowd is, if you are familiar with a set of labs that might be helpful at these temperatures and pressures, please pull myself or Jenna aside and let us know who they are so that we can reach out and interview them. Ultimately, we'd like to have an online sort of Rolodex of who's out there operating at these temperatures and pressures with these materials. All right, so with that, questions for Trenton?
Let Susan ask me a question.
All right, he said no, Susan. That means give him a hard one.
Oh, come on, Trenton. It won't be that bad. So a lot of people have emphasized horizontal drilling as being an important component of EGS. Clearly, you've given us some other options, but how important do you think being able to turn 90 degrees is to being able to create an EGS reservoir?
Yeah, I don't think 90 degrees. So that really is a holdover, I think, from the oil and gas industry, right? They turn 90 degrees so they can stay in the source rock. It is surprising to me that Fervo, decided that 90 degree was a requirement for them as well. That's partly because they want to stay in that temperature window, because if they go too hot, if they incline, more than that, it'll just get too hot for their equipment. So they want that 1,000-meter reach or even more in their reservoir and not hit the maximum temperature. I think for us, hopefully we won't have this maximum temperature we have to avoid. We can just keep getting hotter and hotter. So maybe it's, 70 degrees from vertical is the right answer. Or, now that I'm at Quays is going to be very good at drilling vertical wells. We don't know that we can drill horizontally. So I think there are definitely ways to stimulate vertical wells also. I think the nominally ductile rock model is kind of one of those ways. So I don't think, short answer, I don't think horizontals are necessary.
We have another question here.
Yeah, John Ludden from the Craftler project. It's actually not a question, it's a reply to you, actually, because to an extent, this looks very US dominated, Iceland dominated, what we're seeing here. In Europe, I can cite the Swiss, the Bardrello project, which is an underground laboratory project focused entirely on seismicity, following up from Bâle. So that's going ahead. That's happening now. It's worth looking at. And then if you look at some of the volcano people, so you take the University of Munich, who used to focus entirely on volcanoes, they're now starting to switch and move towards projects such as we're talking about here. So the University of Munich is well worth looking at in terms of testing at scale almost, right? Okay, so those are two European examples that are worth looking at. Thanks.
Yeah, and we have been working with EPFL as well, so that's a Swiss lab.
Other questions? All right, I think we're hungry. Oh, sorry, Sarah's got a question.
You, at one point, Trenton mentioned when you're going through the different techniques that they were using you mentioned hybridization of some of these techniques or combination. Would you like to comment what kind of techniques would you hybridize and how, and what would they result in your opinion?
Yeah, so I think, fracture initiation at the wellbore, that's going to be a bottleneck, or there's always going to be issues with near wellbore permeability that we want is to be in the injector at least as high as possible, maybe not in the producer. So I think creating a tensile fracture at the wellbore is important, and how big that is, maybe we can drive it out 20, 30, 100 meters. And this is at both Forge and Fervo, their fractures are going, say, 100 meters or possibly more. But I think the hybridization is going to start to occur when we get, far from the wellbore, that those tensile fracts are going to start to be branching, interacting with natural fractures. We'll start to get, with time, thermal fracturing. And so I think that, to me, there's a question is, wellbore spacing is going to be a huge, the further apart we can have our wells, if we can have 500 meter spaced wells, that will be a far more sustainable system and higher, well, maybe not higher flow rates. We may have to trade flow rates, but I think sustainability is going to be, dependent upon fracture or well spacing. So if we can get fractures to intersect somewhere in the middle, along more of a network of fractures through, natural fractures, and secondary fractures, I think that's where I think the hybridization occurs to allow us to go further distance. Because Fervo and Forge are both at this 100-meter distance. I don't think their systems are going to last more than 10 years. They're going to have breakthrough before that. So, to me, the hybridization allows us further well spacing.
Thank you.
All right, there is one more question, and then I will dismiss you guys for food. One moment.
Hi there. My question would be, let's say you achieve drilling the 10 to 15 kilometers that you plan on doing into the high temperature resource. What do you plan on bringing the heat up to the surface with? What type of fluid are you going to use to maintain the supercritical nature of that heat all the way to the surface?
So I think it's just going to be water, and I think the fluid working fluid in the reservoir will probably always be water. Maybe supercritical CO2 is possible, but that's going to take a lot of effort to dry out the reservoir, so you don't have these caustic fluids. I don't think it's important that we keep it supercritical from the reservoir all the way to the surface. I think it's probably going to lose the pressure. We're going to trade that pressure at depth, to lift the water to the surface, and it may come out as superheated steam. So I think the supercriticality of the fluid at the surface is not a requirement, but it will maintain its enthalpy. So unless it's cooling much into the rock, which it won't after a while.